today I'm going to talk about Moshi, which is a kind of a foundation model for conversational speech. So this is joint work with some colleagues at QTI. And so QTI is a new non-profit research lab in Paris with the goal to develop to do some AI research and to develop new models. The goal is to publish as much as we can, basically to publish everything, not just code or not just models, but also papers, etc., to really explain what we do. Okay, so maybe let me start by explaining what is Moshi quickly. So this is a conversational AI model. And in that sense, it's kind of a multimodal LLM in the sense that it can process at least two modality, which are text and audio speech. And the goal with this model is really to mimic real human conversations. And by that, I mean trying to capture as much as possible what a real human conversation look like. And I'll come back to what I mean a bit later. And so because of that, we tried to make a model that was really focused on this conversational aspect and not so much about knowledge or reasoning as a lot of other large language models are doing nowadays. And so because of that, the model is really not the best at this kind of things. So maybe I can show you a quick video showing what is Moshi in practice. And so in that case, basically there's two instances of Moshi that are running on MacBook laptops, and which are talking to each other.
Oh, hi. Well, machine learning is a field that uses algorithms and algorithms to perform tasks like recognizing patterns and making predictions based on data.
Yes, machine learning is a powerful tool that can help us make sense of large amounts of data.
That's right. It's really useful for things like predicting customer behavior or detecting fraud in financial transactions.
That's right. Machine learning algorithms are used in many different applications, from medical diagnosis to weather prediction.
Yes, it's versatile. It can be used in everything from self-driving cars to personalized recommendations.
Yes, it's amazing how far machine learning is.
Okay, so that was Moshi. And so actually we open source the model, and there's two versions of the model, one with a feminine voice and one with a masculine voice, and that were the two instances running. Okay, so you might ask, wait, how is this new? We already have conversational and assistant. We've had those for years, probably more than 10 years now, with things like Google Assistant or Siri or Alexa. So I think there's a pretty big difference between what we're trying to do and what we have with this existing model. And so some of the reason is how the existing conversational model are working. So in a traditional voice, typical voice assistant, basically they are broken down in 4 steps, which start with voice activity detection. So the idea here is really to detect when the user is speaking and also when the user is done speaking. Once this first module has identified that, there's a second module, which is automatic speech recognition, which basically will transcribe what the user just said into text. Then you can apply your favorite large language model to get an answer to the user query. And finally, you can apply some text-to-speech module to synthesize speech back. The problem with that approach is that because you have this sequential module, this will tend to induce a lot of latency. And so typically in existing voice assistant, you have from 3 to 5 seconds between the end of the query from the user and the beginning of the answer of the assistant, while in practice, in a human conversation, the time between two turn of conversation is much smaller and quicker than that, and is usually around 200 milliseconds. It depends on the languages, but in average over like different languages, that's around this. So we can already see that it's significantly shorter than what we can have with existing assistant. And the other thing is that we have this text bottleneck in the middle, which means that we lose a lot of information, because speech and conversation is much more than the text and especially the transcript of what is said. And in your voice, you'll have hesitation, you'll have some intonation, some sentiment, etc., which are important information if you want to interact in a natural way. Yes.
These 4 steps are done secretly. I think that it seems that the first 2 steps and the last 2 steps would be very similar. Example, we get the last 2 steps seems to be almost.
Yes. No, it's so it's definitely true that you can start doing the speech recognition at the same time as you're doing VAD, and same thing if you have like a streaming language model, you can start like generating speech, and which is actually what is done in the existing model. Otherwise, the latency will be even bigger than that. But the point is that in automatic speech recognition or text synthesis, speech synthesis, usually you still need. So typically in most text-to-speech, you still need sometimes a full sentence or at least like a couple of words to be able to start generating audio. And in the same way in ASR, usually you need at least like 2 seconds of audio to be able to start doing the recognition. And so if you add all those things, you still end up with this like few seconds of latency. And of course, you can, like right now, people are trying to squeeze as much as possible from this pipeline, and you can actually reduce the latency. I think without too much effort, you can probably get something to like maybe 1.5 to 2 seconds, but it still requires a lot of like custom ASR, text-to-speech, etc. And you still have, I think, it would still be very hard to go lower than this 1 to 2 second latency. And more importantly, I think if you have like a model that has these different steps, and especially if you still have this voice activity detection module, which will determine when the user is speaking and when the model is supposed to speak, this means that you still have something which is a turn-based conversation, where either the model is speaking or the user is speaking, but you cannot have both at the same time. And in practice, a real conversation is not like that at all. And you'll have actually a lot of overlap between the speakers. And so again, depending on the culture and languages, this can go from like 10 to 20% of overlap, but there still is this overlap. And this overlap can be different kind of things. So that can be like, for example, the user that want to interrupt the model. So for example, if the model did not understand the question correctly, you would like to be able to interrupt and have the model answer, like handle this thing nicely. It can also mean like finishing the sentence of someone else. It can also mean like agreeing to something that the other speaker just said, something called back channeling, and which is typically something like or okay. And so there's also a lot of these things in real conversation, and this is the kind of things that we wanted to capture typically. And so typically communication is more than just text, and we'll, as human, will listen, speak, and think at the same time, and we don't have like this different like process when we listen to what the other is saying, and then we start thinking about what we'll answer, etc. We do all that at the same time. Again, we interrupt each other. And as I said earlier, there's a lot of information that cannot easily be retranscribed in text, such as emotions or tone that we would also like to capture. And so for that, we would like to develop a model that is able to capture all of the things, and because of that, to be a multimodal model. And we want to capture all these phenomena that I just described. And so why is this a hard problem? So first, it's hard because, as I said, if we want to have something that looks like a conversation, this means that we need very low latency, around 200 milliseconds. Second, we want to be able to handle the overlap between the user and the AI. So this means that we cannot have like this kind of like voice activity detection and turn-based conversation. And the last challenge is the fact that compared to text, having access to speech data is very hard, and especially to conversation data when we have like the both side of the conversation. And I'll come back to that later. Okay, so now let me explain how we solved these challenges, and basically what is the overall architecture of Moshi. So of course, Moshi will be based on an autoregressive language model. And we will use discretized speech representation so that we can treat them as regular tokens, like regular text token. And the second thing, which is probably one of the main contribution and innovation of this model, is to model multiple streams in parallel. And so basically, we will have 3 streams of data. The first one will be the input, the audio input from the user. The second stream will be the output, the audio output of the model. And finally, the last stream will be the text corresponding to what the model is generating as audio. And so we will model these 3 streams in parallel, which means that we can, at the same time, the model can both listen to what the user is saying and generate speech at the same time. Of course, this means that at most time when the user is speaking, the model will generate silence, but it will still generate some audio output at every time step. Okay, before diving into each elements of Moshi, let me very quickly give a background on large language model, which, as you probably know, are probabilistic models that basically aim at predicting the next word given the context. And to do that, basically, at each time step, that they will predict a distribution over the vocabulary, and then you can sample a word or take the most probable word to decide what you'll generate as the next token. And with that, you can basically design model like ChatGPT and stuff like that. So can we just basically replace text by audio and try to directly generate audio in that way by taking audio as input and autoregressively generating the next frame of audio. So that's an approach that's been done and tried in the past, but doing this naively and directly from the waveform is doable, but is kind of challenging. And so if we take, for example, the sentence "QTA is an AI lab based in Paris," with most like existing LLM, this will probably be 8 tokens or so. And in audio, depending if you speak fast or slow, let's say it will be around like 3 seconds. So if we sample our waveform at a frequency of 24 kilohertz, this means that for these 3 seconds of audio, we'll need to generate 72,000 values. So this means basically that we need to make 10K times more prediction than text if we generate audio in this way. And so, of course, we could change the sampling rate of our signal. We can use like architecture such as dilated convolution and stuff like that to try to make this more tractable, but we'll still need to generate thousands of values and make thousands of prediction for each second of audio, which would be very hard to do in real time. So instead of doing that, we'll try to basically compress the audio to something that's smaller and probably easier to model thanks to that. And so compressing audio is something that we've been doing for a very long time, and with things like codecs. And so here the idea would be to use a codec to obtain a compressed representation of audio and speech in our case that's easier to model and more tractable in practice. So here, what we'll do is we'll use a neural codec, which is basically an audio codec based on a neural network. So how do these codecs work? So basically, they are auto-encoder with reconstruction and or adversarial losses for training. And they use something called residual vector quantization to have like a discrete bottleneck between the encoder and the decoder. And basically, this is the way to represent and compress audio, is to quantize the representation, the output of the encoder, and to transmit the discrete representation of this step. And so basically, we take what we obtain when we perform some quantization are code words. And so when using a codec, you would transmit the code word and reconstruct based on the code word on the other side. Here, what we'll do is we'll take the code words and use this as audio tokens for audio language modeling. And so basically, we'll apply standard auto-regressive models on those audio tokens to have a generative model of audio. So what is residual vector quantization? So basically, the easiest way to perform vector, one of the easiest way to perform vector quantization is to apply an algorithm such as k-means, and then you can represent each vector by the centroid to which it is associated. And in that case, the indice of the centroid would be the corresponding audio token. The problem is doing that on high dimensional vector doesn't work very well, and especially because you would probably want to have like a fairly large number of centroids, and unfortunately that doesn't scale well to increase the number of centroid in a flat way. So instead, what we can do is we can apply k-means a first time. Then we take the residual, so the difference between the quantized vector and the input, and we reapply k-means. And we do that a few steps. And so at each step of the process, we get one centroid or one code word. And this will give you basically a discrete representation of our signal. So the good thing also with RVQ is that this gives kind of like a hierarchical representation, which means the more we advance into this into this process, the finer the details are. And so basically we have something at the first layer of RVQ which is very coarse, and the more we advance, the more detail we get. So that also means that we can actually like stop the process at only half of the number of steps that we would apply, and we can still reconstruct a pretty good signal based on that. Okay, so as I said, we can take the representation from a codec and use that to perform language modeling directly. Unfortunately, only using tokens from a codec does not work very well in practice. And what do I mean by that is that typically this will not capture the high-level structure well. And so it means that the speech that will be generated will not contain meaningful content. And so I can give you an example. So this is not, so this is from previous work, something called Audio LM from Google. Wait.
And for Annie, outside that, it was as though a dark cloud was conjunction. She can also kind this went also of a doctorate of.
So the beginning basically is a prompt. So at the beginning there's a 3-second prompt, which was like the natural, like the speech that sounded like speech, and the end was what was generated, and you could hear that it was completely nonsensical. It sounded like speech, and so actually it captures things quite well, like the voice of the speaker, his way of speaking, etc. But it did not capture at all the content of the meaning of the speech. So what was proposed in the past, and actually in this work called Audio LM, was to use a second kind of representation of audio that did not come from a codec, but that come from a self-supervised model. And so here you can think of something like a bit like BERT typically, but for speech. So basically what you would do is you would encode your speech typically with CNN to downsample your speech. You would get like a representation, let's say every 10 milliseconds, and then you would mask some of those representation, and you would try to predict the representation back, either with a contrastive loss or with something like BERT, where you would try to predict an index corresponding to this representation, and this index could be like typically like a clustering of the input signal. And so the good thing is with semantic token is that they capture like the high level structure of speech very well. And so when you generate with something like semantic token, you would have like something that really captures meaning quite well. But the problem is that this representation, you cannot really reconstruct speech with it, and you tend to lose a lot of information from the speech, such as like a lot of information about the speaker typically, so how the voice sound, the recording condition, etc. And so here is an example. And so basically, AudioLM proposed to use both acoustic and semantic tokens and generate first the semantic token and then the acoustic token. And so this is the kind of results that you could get by doing that.
Some images, like some sensations, which produced by the light of nature in all creatures, are subject to various conditions, as in the.
And so here, what you get is basically something where you would have both the high audio quality that you would get from the acoustic tokens and also more of the meaning and from the semantic token. Okay, so here in our case, yes.
From what I get, acoustic token is like a way to take the speech data and to split it into discrete, or to map it to a discrete vector space. Whereas semantic token, for me, it's a way, from what I understood, it's a way to train like language model on top of this. But basically, I don't know. I don't understand why.
Yes.
Not one thing you put on top of the other.
Yeah, because I went a bit quick over that, and so actually you're totally correct. So basically, what I described is the way to train the self-supervised model, and then typically what you would do is you would take this model, take one layer in the model, typically in the middle of the model, take the representation corresponding to that model, and then you apply k-mean on that to get discrete representation again. And that would be a semantic token. And so because usually this self-supervised model, they have like, I think like one frame, like the sampling is like the frame have a frequency of something like 50 Hertz. And so you would get like 50 such token per second. Okay, so here, what we wanted to do, and actually that was also proposed by previous work, is to kind of like merge the semantic and the acoustic token. So one way to do that is to actually take like this semantic token from a self-supervised model and basically to distill this to add the distillation loss on the first codebook of your neural codec. And so in that way, then you get a codec that also kind of capture this semantic token, and you don't have to have like two models to be able to have both semantic and acoustic token. You can only use a single codec. So most existing codecs worked at usually around 50 Hertz, and also were non-causal. So being at something like 50 Hertz means that you even though it's way less than the 16K step that you would need to generate 1 second of audio, it's still 50, at least 50 autoregressive steps per second. Actually, it can be even more than that, because at each time step, you have to generate more than one token. But if you have typically RVQ with 4 level, you have to generate 4 tokens for each step, which would mean 200 generation per second. So this is still hard to have a model that would be real time with that amount of forward pass to do per second. So we developed our own neural audio codec, which is fully causal. So why do we need something that's fully causal? Because if we want to be able to again to have the lowest latency as possible, we want to be able to start generating as soon. We don't want to have to wait, let's say, like 100 milliseconds in the future to have like the representation of the frame. So we can only rely on the past to get a representation of the audio. We use we distill semantic tokens into the first step of the RVQ, and we operate at a fairly low frequency of 12.5 Hertz, and we have 8 code books per step. So it means that in practice we can compress speech at something around 1.1 kilobit per second, which is quite low. And existing codec, especially codec for voice, tend to operate at a much higher rate than that. Okay, so now that we have tokens, we can start applying standard language modeling techniques to this sequence of token to generate audio. So what we could do is we can take our sequence of token, flatten it, and predict in that way. So the problem with that, as I was just mentioning, is even with our new codec, at 12.5 Hertz with 8 code books, it means that we still need to generate 100 tokens per second, which means 30K tokens for 5 minutes of conversation. And so trying to be real time and generate 30K tokens in 5 minutes is actually quite challenging. So we explored other ways to generate more efficiently. So one thing that you can do is, instead of predicting the different step of the different layer of the RVQ sequentially, you can predict them in parallel. And so basically, you apply some form of pooling on your input. You feed the pooled representation for a time step to a big transformer. This will give you a representation, and then based on this representation, you have 8 heads to predict the eight tokens corresponding to the 8 levels of the RVQ. The problem of doing that is we lose all the dependence between the tokens of the same time step when we generate. And because of that, the quality of the audio that we generate really suffers from doing something like that. So instead, we did some sort of hierarchical generation. So for the input, we did exactly what I just described, which is basically we pull all the embeddings of the different acoustic token or audio token for a time step. Then we apply a large transformer, and this will give us a representation to predict the next acoustic tokens. And now, instead of directly generating the 8 token in parallel, what we'll do is we'll apply a small autoregressive transformer that only take as input this representation from the big temporal transformer and autoregressively generate the 8 tokens of a particular time step. And by doing that, we only have to apply the temporal transformer 12.5 times per second, but still have like still keep some dependence between the acoustic token of given time steps. Okay, so with what I just described, we have basically a continuation model, so a model that can take the beginning of a speech sequence and complete that sequence. And so but this is still not really a dialogue model. And especially if we want to take that model and transform it into a dialogue model, we could do something a bit like what's done for ChatGPT or a text conversational model, which is basically to concatenate the turns of the model and the user. But if we do that, we still have a turn-based conversation model. We still need to determine when the user is done speaking and the model can start speaking. And we cannot have overlap between the two. So basically here, what we did is we decided to overlap, to model the two streams in parallel. And so basically we'll have the audio token from the user, the audio token from the model, and we just concatenate all those tokens, feed those as input, apply our large transformer, and then at each time step generate the audio output from the model. We had a third stream, which is the text corresponding to the model audio. And so the reason for doing that is, as I was saying earlier, we don't have a lot of speech data, and which means that if we try to train a model only on speech data, the model would not have a lot of knowledge, and it wouldn't be super interesting to talk with that model. And so basically, we still need to rely on text a lot to acquire knowledge. And so adding this third stream of text data helps to align basically the representation of the text and the speech modality, and make sure that the speech modality can use all the things that were learned, or most of the things that were learned from the text data. And again, like this, showing that using yes.
What about YouTube data? Is it copyrighted?
So we could use YouTube data. So first, there's a lot of YouTube data that doesn't contain speech, which is music, or and also we looked a bit at it. There's a lot of rather low quality. You don't have a lot of typically like podcast or stuff like that in on YouTube. You have some, but a lot of it is not a high quality speech. And also, I think so. First, also, like there's a lot of this data that we might not be able to use because of copyright, etc. And also, YouTube is kind of like limiting how much you can download from it, so it would be hard to get a big data set out of it quickly. And I'll come back to kind of like data a bit later. And so again, so as I was saying, so previous work already showed that text using some sort of text help a lot to generate good quality audio, especially so some work showed that typically using like a text prefix, like the text corresponding to the audio in some sort of like kind of like TTS helped a lot to generate more high quality audio. But what was done was usually to either interleave like text and audio, but which in our case would be hard to do, because then it would be very hard to have something that would be real time. It would be very hard also to handle interruption nicely. So instead of that, we decided to really align the text with the audio and to basically see the text as an additional stream, which means that in the text stream, we had to add some padding token because usually for a particular audio, like the number of tokens that we get for the transcribed text is way lower than for way lower than for speech. Okay, in terms of training, so as I said, we started from text only data. So here we trained a regular large language model with 7 billion parameters. We trained it on around 2 trillion text tokens. Then we performed some audio pre-training. So here we used a single audio stream. So we basically downloaded a lot of like audio data, like speech data from internet. So a lot of podcasts and stuff like that. Around 16 million hours. And so we trained basically just a continuation model on that data, plus some still using some text data. Then we started what we call the kind of like the post training, in which we started to try to teach the model what a conversation looks like, and so typically what terms of speech would look like. And so for doing that, we took the data from the previous steps and we applied some diarization to get multi-stream data. So basically diarization is something that will tell you at each position in your speech stream what is the speaker talking at that particular time. And so based on that, we separated we picked one of the speaker as the model, and everything else was going to the user stream. And so we trained the model on this fake multi-stream data. And fake in what sense? In the sense that with diarization, you don't get overlap between the speaker, because basically at each step, the annotation that you'd get is a single speaker talking at that particular time. So basically, so what does this mean? It means that you don't have overlap, and so the inactive speaker, especially the model, is perfectly, or like not the model, but the user also is perfectly silent when the model is speaking. And so in practice, we wanted to have some robustness in the sense that if the user was doing some back channeling or stuff like that, this would not interrupt the model. So finally, we needed to fine-tune the model on true multi-stream data. And so for that, basically, we recorded some human, like with 2 microphones to have like a true multi-stream data. So basically, we hired humans to have like conversation, and we put them in 2 different booths and recorded them separately to have like real conversation with overlap, etc. Of course, we couldn't acquire a lot of data in that way. So what we did is, based on that small amount of data, we trained some TTS model that could generate multi-stream data. And then we generated fake transcript and synthesized those with our multi-stream TTS data. And so we got around 90K hours of this mix of real and synthetic multi-stream data, and we finally trained the model on that.
Wondering if you are talking about single language data set, or you're dealing with multiple languages?
So right now it's only English, yes, and we want to extend to other languages. So maybe I can skip this slide. Oh well. I'll go over it quickly. So to generate this kind of like speech synthetic data, we wanted to do some sort of also some instruct where you could ask, the model question or give small tasks to the model and have the model respond to those. So we generated a transcript with a model that actually a custom model that was also fine-tuned on transcript. So 2 reasons for that. So first, we looked at using existing text instruct data and just synthesized this. Unfortunately, a lot of like the existing dataset are not suited at all for conversational speech. One of the reasons is the lengths of the terms are quite long, and so usually, especially with recent instruct data, the answer from the models are usually quite long. And so in speech, that would be very annoying if every time you ask the question, the model takes 2 minutes to answer. That I think that the experience wouldn't be great. And the second thing is a lot of these data sets contain a lot of things that not well adapted for speech, such as bullet points and symbols that are hard to transcribe. So instead of that, we train the model on real transcript from the real conversation that we recorded, and then we synthesize them with the multi-stream text to speech. It's also at that step that we can make sure that the model has a consistent voice, because basically for that, when we generate that data, we always use the same voice for the model. And this is the voice of a voice artist that we worked with. For the model that we open sourced and we released, we changed the voice a little bit so that it doesn't sound exactly like the voice artist. And we also recorded some like different emotions, like being happy or sad or speaking like with a pirate voice. And so that you can give instruction to the model and ask the model to speak with that particular expression or kind of talking. Okay, so let me briefly talk about experimental results. So first, evaluating these models, unfortunately, is quite hard. So already, like as you probably know, like evaluating text LLM is becoming harder and harder, and I think it's even harder for speech model. One of the reasons is that if you want to do some human evaluation with text model, you can produce you can take 2 models, produce like the answer with both model, and ask the user to pick the one it prefers. For speech, it's much harder to do that, because it's very hard to hold 2 conversations at the same times, especially when you want to capture stuff like how fast the model answer, does it like handle like interruption well and stuff like that. So unfortunately, the kind of evaluation that we did, I think, is very incomplete and only capture a small aspect of what we'd like the model to do. And so one of these is kind of like the knowledge of the model. And so for that, we took existing question answering data set from like text data set, and we generated some speech versions of those, and we evaluated the model. And so here, the first thing that I want to highlight is the fact that there's a big gap between the model when we use it just using text versus using the audio model. So basically on Trivia QA, with our text model, we got something like 56, an accuracy of 56%. And when we ask basically the same question, except we ask them orally instead of feeding those as text to the model, we only get an accuracy of roughly 23%. So part of this might be because the model don't understand like the question, typically like a named entity or something like that. But also there's definitely a gap in terms of knowledge when we use the model as through audio instead of text. If we actually look at using the model without this text stream, the accuracy drops even lower to something like 7%, which shows that actually like still generating text helps the model a lot to use to use the knowledge that it acquired on text data. And if we don't use text batch in this pre-training, we also see a drop in performance. So basically, there's still a pretty big open question on how to like train a truly multimodal model between speech and text, and make sure that we align the representation from both modality and be able to use all the knowledge from text when interacting the model using audio. I want to keep some time for questions, so let me skip the two other evaluation and briefly mention some existing open problem. So one of these is what I just mentioned, this kind of like modality gap of modality between text and audio. The second, I think, is the generation process that we're using. And so typically, we've been playing with, like temperature and nucleus sampling and like the standard generation algorithm from text. And basically what we saw is if we play with this, usually there's a parameter that will be pretty good at capturing like the naturalness of the conversation. And so making sure that the model speaks when it's supposed to, etc. But then the performance in terms of knowledge drops a lot. And then if we typically reduce the temperature, the model will get much more factual, but also will tend in terms of like naturalness, the model will tend to mark way longer pause, etc., which is not something that we want. Also, like few shots in context learning, I think, is something that we haven't explored at all, and that would be pretty interesting to try to understand what the pre-trained model is already capable of, and whether we can leverage better what was acquired by this model to reduce a bit the need for the instruct data. Okay, so to conclude, so Moshi is the first open source real-time and full duplex conversational AI. I think it's really more of a starting point than an end point in this kind of models, in the sense that there's a lot more to do and a lot of open problem. We published a paper with a lot more detail than what I presented here. That's available on arXiv or on our website. The model, the inference code, and the codec are all open source and available online. And we have a small demo running online if you want to try the model. And that's it. Thank you for your attention.